In this video, I'll be discussing how we add, subtract, and multiply matrices by a scalar, and additionally, we'll get into a little bit about why that might be useful. But before we get into all that, matrices are unique mathematical objects which are different from individual numbers and normal variables. And they have their own rules for how we work on them. Like in the real number system, for example, we have like properties of equality or additive identity, multiplicative identity, specific numbers that have particular purposes. And in matrices, they have similar such entities and objects, which are often predefined in the book, and that's kind of, and we'll get into a little bit about their relevance as we progress through the next few videos. But the property of equality states that two matrices are only equal if they're exactly the same. So, like when looking at previous matrices, say for example this weird matrix A that I made up in the last video, it could only be equal to exactly the same matrix of those 12 numbers with the exact same dimension. So like its transpose, we would not say that it's equal to its original matrix, even though it has the same numbers and the same amount of elements. It also must have the same size, and every element must be equal to every other element of that same matrix. So for example, a 3 by 3 matrix could never be equal to a 2 by 4 matrix or 1 by 9 matrix or whatever, because it first of all must have the same size, and also it must have everything exactly the same. But we use the exact same equal sign, like say for example we wanted to know, is A equal to B? Well, obviously not. And we could write that in a traditional mathematical sense as, A does not equal B. And we could only say that A is equal to B if those two matrices were exactly identical. And as we move to addition and subtraction, they operate in a very similar ways in that we're only allowed to add or subtract matrices that have the same dimension, they have the same size. So, and that's just a matter of needing to have the proper number of elements in order to combine them together. Now, they don't have to be the same matrices to be able to add them. But like for example, say we wanted to add matrix A and matrix B, we would be allowed to add them together because they have the same number of elements. And say the same thing if we wanted to do C minus D, that would be an allowable matrix operation because they have the exact same dimension. But say, for example, I wanted to take these two matrices, A plus B, and add those together. That would be impossible because they don't have the same number of elements. Now you could theorize how you might do that, or you could make them the same dimension by filling in missing elements with 0, and those type of solutions would technically work. But that sort of matrix math is just not allowed because of the mismatch in dimension. So let's do a few examples and talk about how you actually would add them together. So say, for example, we would want to do A plus B. To add the matrices, you're going to add each respective element in the same row and column from the two matrices together. So basically, in the first row, first column, A11 would be 2 and B11 would be 1. We would add those together in A plus B. So I'm kind of imagining taking, the first element of each matrix, that one, and adding those together, and that would be in the sum matrix A plus B. So the first element of this new matrix would be, well, 2 plus 1 is obviously 3. And then moving along, I would get the rest of the elements by doing the same thing. I was trying to make a little bit more room there, but I guess that I'll just make do. So then the second, in the second column, first row, I would have negative 3 plus 0, which is negative 3. And that would be, the next element. The order that you do it in doesn't particularly matter. Usually how we like to do it is go first row, second row, third row. But as long as you're adding each correct element to the respective element, you'll be fine. And then so in the next row, first column, 0 plus negative 3 is negative 3. 5 plus 1 is 6. 7 plus 2 is 9. And negative 1/2 plus 2 is 1.5. And like with normal mathematics, you could express your answers as decimals, fractions, whatever form is fine, whatever you find preferable. So I just went ahead and did it as a decimal instead of a fraction, but you could leave it as fractions if you wanted. And subtracting goes exactly the same. You'd take every element in, say for example, we wanted to do C minus D or A minus B, you would take every element in this matrix and subtract every element in this matrix. But also one thing, with subtraction, make sure that each one is to be subtracted. So like again, I would have my new resulting matrix would be the same dimensions, 2 rows, 3 columns, 2 by 3, whereas this one was 3 by 2 because I was adding together originally 3 by 2 matrices. But I just want to be careful to subtract each one. So 7, in the first row, first column, 7 minus 6, that should be 1. And -3 minus 0 should be -3. But if I was, say, going to do 0 minus a -6, don't forget to distribute the negative. Basically, each of those signs would change because subtracting a negative is the same as adding. So 0 take away -6 would actually be 0 plus 6, or 0 plus 6 is 6. Then 0 minus 8 is -8, because again, I'm going to be careful to subtract. 1 minus 1 is 0, and 5 minus 9 is -4. But otherwise, all normal rules of math apply to each individual element. So one way I could think about subtracting in a matrix is, as distributing the negative. The negative would be distributed to each term, and then after I distributed that negative, it would add. So be like 0 plus 6, 0 minus 8, 1 minus 1, or 1 plus a -1. However you want to think about that, just make sure that you are indeed subtracting each element of the matrix. And now another thing is, well, why would I think about adding or subtracting matrix, and what would be the value of doing such? And there's a lot of different geometric reasons why you'd want to do that. But a very simple way would be, say we take the original example in the last video of a particular object mapped by a matrix. Let's say I wanted to take this lightning bolt and move it up 1 unit, or move it right 1 unit. It's very simple to do when adding the proper matrix. Now, an idea you might remember from transformations is that if we, say, add 1 to the y values, that would move the point up. So I could think about, in that matrix, like, let's just say I was to put +1 here. Like, another thing about adding with matrices is, in order to add to a matrix, it has to be the same dimension. So if I wanted to take this matrix, which represents this particular image, I could not just add 1 to it, because it has to be the same dimension. So it would have to have, well, 1, 2, 3, 4, 5, 6, 7 rows and 2 columns. So we need to make sure to add it to a 7 by 2 matrix. But basically, let's say I wanted to move it up 1 unit. How would I do that? Well, let me just write it down and then try to explain my thinking here. The matrix I would want to add to this is, let's just say that original matrix was L for lightning bolt. I would want to add the matrix 0, 1, 0, 1, 0, 1, 0, 1, 0, 1. And what this matrix sum would do is it would move the image up 1 unit. And to think about, well, why would that make sense? Let me move this back over here. But basically, if I was to add 1 to each of the y components, if I was to take this matrix and add it to that matrix I wrote right there, what would happen is, well, I would get 0, 1, -2, 4, 0, 5, 2, -1, and so on. But basically, adding 1 to all the y values would move each of those points up 1 unit, right? Because if I add 1 to the y value, it's going to be up 1. So it's kind of sensible that that this matrix would be what we often refer to as a translation matrix, would move it up 1. Or of course, if I added it to the matrix of 1 zeros in the same way, that would move it to the right 1 unit. Or say I wanted to take away this matrix, it would move it down rather than moving it up. And we could use matrix addition and subtraction to move that image all around. And say I was developing a video game where I wanted an image to move to a particular location, be very simple to do, even in a 3-dimensional sense, where you would just need to add an additional third component to those matrices. Instead of being, 7 by 2, I could make it 7 by 3, and then we would have 7 points in 3-dimensional space, which make up a 3D polygon as opposed to a 2D one. But I think that's good for this video. In the next video, we'll get into scalar multiplication and do a few more examples of basic matrix algebra.